in the So I've got 4 or 5 problems from the book. They start from chapter 4, they go to chapter 5. There's no chapter 3 on the midterm. There is a little bit of chapter 2 Smith-Charty stuff on there, but it's all concept. So let's just get to it. A hemisphere, everyone knows a hemisphere is a half a sphere. It's not a quarter. Got burned by that before once. A hemisphere has an electric flux density of, I'll write that a little prettier. D is in the capital R hat direction, so it automatically tells us we're in spherical for this textbook, right? And it's rho naught R. So it's in the R hat direction, and the further we are in R, the more the D field is. And then this rho naught means we don't know if it's a line, an integral, or sorry, a line, a surface, or a volume yet, but we can sort of infer that it's a volume because we're in a sphere. Everybody sees that? The further we are in R, the bigger the D field is. And at 0, it's 0. Yeah. But it's a hemisphere. So if we say that I have a sphere and I have a center point, then I'm slicing this in half. And I've got half a sphere, right? And so I've got this R, and the further I am out here, most of my D field's along the outside, and it fades in linearly. That's all this means. Okay. If I give you what R is, and I did 95 centimeters, and I give you that rho naught is 100 coulombs per meters cubed. Well, first of all, we already know that if it's in meters cubed, over meters cubed, that's a volume, right? Cubic. Find the amount of charge inside. Who knows exactly what to do before I show you the answers and stuff?
Integral.
Hmm?
Integral.
Yes. Integral of what?
T.
Hmm?
D.
Not precise.
Oh.
You're going to integrate the hemisphere, right? So, the amount of charge Q is a volume integral of our volume charge density in dV, right? But we can't use this yet. dV is, we know we're going to do this in spherical coordinates, right? So if this is a cube, like it is in the textbook, our dV is just dx, dy, dz. Boring, right? Easy, but boring. When we do a triple integral dx, dy, dz, I think the textbook is like a cube with 2 meters on each side, so you'd have some 0 to 2, 0 to 2, 0 to 2, rho v, dx, dy, dz, calculated. It's too trivial, so I made it a hemisphere. Because what I want you to remember is that when you have dv in spherical is dr, sorry, give myself some space. It's dr, d phi, sorry, d theta, d phi. But there's crap we have to put up front, right? We have this r squared sine theta up front.
The R and theta are in different positions on the page there. Are you integrating them in a different order?
This can move around.
Okay.
The other ones can't. But I'll stick with the with what it looks like there. So if we remember, d theta has 1r, d phi has r sine theta in it. So when you multiply them together, you get the r squared. So when you do this dv, that's what you're stuck with. So when you do a triple integral in a spherical volume, yes, you're going to do dr, d theta, d phi, but you also have to have this r squared sine theta out front. And if you forget it, it'll be way wrong. In fact, if you forget the r squared, your units will be off if you put in units in your calculator. So, I didn't cover anything that Nick doesn't already know, because he's Mr. Math. So, doing a triple integral on a hemisphere. So our integral looks like this. So we have Q, and I did R up here for R, and I worked inwards, right? And if this was a whole sphere, then this middle one would be at 2 pi,
Yeah, that's what.
right? But we're only gonna go halfway, so it's only 1 pi.
Oh, okay.
This one, unless it's a quarter sphere, is gonna be always pi. It would be, if this was a whole sphere, that would be R, 2 pi, and 1 pi. Right? If you do that, if you go twice around it, it doubles. You don't want to do that. So that's exactly what we've got. And we've got our d theta, which is this integral, our d phi, which is this integral, and obviously dr goes from 0 to r. Okay, now we can just plug numbers in. And if you did that, you should get that number. So since this is a final review, you don't have to do it right now, because I know you won't. Every time you guys ask you to calculate, you guys never do it. But go home and make sure you can get that same number, and you'll be good. So the real question is, will you remember? I mean, you'll have this obviously to do, but anytime you're looking, you have a D field. Your D field has to be, you have to be given some rho V, some rho in some kind of case, some kind of charge density distribution. You integrate that over the volume that it's contained in. But that charge density in this case, it's a static number. It's just 100 C per meters cubed. But it's not in this hemisphere. It's not evenly distributed, right? Most of it is on the edges of the circle, right? Around these edges here. And then as we get to 0, there's nothing in the center. It's really weak from the center, and then it gets bigger, bigger, bigger. If this were a whole sphere, what do you expect the answer would be? And what makes you confident saying that? It's intuitive and it's the correct answer. I guess what would make that the wrong answer? If your charge distribution wasn't just in the R direction. If it was, this half is something, and there'd be some extra terms in your actual flux density here, but this is all in R, so it's just even across all of R.
Could you also say because the shape of the object is very equilibrium, kind of like from the sphere, from the center to R?
You could, but this particular D field, if we made a whole sphere out of this, it would be even everywhere. But if I added some term to it, I don't know, minus phi hat, rho naught, phi, who cares? Then at phi is 0 and 360, and then you'd be some negative value over here. So it would be offset. It would be totally different depending on where you were. It would still be stronger on the edges, but it would also vary with where you are, or it could vary along this axis too. It could vary on either for phi or theta. But in this case, it doesn't say that. So yes, it's double. It would be double if this is the whole sphere, but you can't just go, oh, well, it's half a sphere, so it's always just double if we were making a whole sphere.
This one is evenly distributed.
This one happens to be evenly distributed with respect to the angle, not with respect to R. Okay. So find the electric potential, the voltage, fancy word for voltage, at a point at a distance v from the origin in the xy plane due to a line charge with charge density of rho L and a length L. The line charge is coincident with the z-axis and extends from negative L over 2 to positive L over 2. All this is saying, and I drew it for you anyway, but the word problems, especially in our book, they put it in words and then they put the picture for you. So in light blue, there's my charge density. That's my line charge. And the dark blue is just my axes. And I'm going from L over 2 to negative L over 2. So I've centered, it's L long, obviously, but I've centered it across the y-axis. It's coincident with the z-axis, it just means it's on the z-axis. And then I have some point B here that I want the voltage at. All that says. And what they're asking for is an expression of what the voltage is at this point. Now the voltage is going to be dependent. This little tiny bit, if we were to zoom in on this, this charge density, and it looks like this, it's kind of fat, right? I mean, it isn't, but, and there's our z-axis. And B is way over here. That little slice contributes to the voltage seen at B. So it has its own, let's call it R prime, right? And this little slice is gonna add to that B, and so on, all the way down. But they're infinitesimally small, so we have some delta dz, or we just call it dz, I suppose. Right, and we have dz's all the way down, so we're gonna integrate on a line, right? Because that's the most accurate way of doing that. And as we integrate, if we look, if we were here, that B, or this R prime is shorter than that one. So our R prime length is going to constantly be changing. So we're just coming up with an expression for now of what the voltage is. So equation 4.48c, and that was in a different edition, so it may be different for you. There's an equation for what the voltage at some distance from a line charge is. The book's full of equations. And like I said, the chapters are pretty easily read. You go look through the equation and you're like, oh, that's what I want. And it tells you, this is what this is for. Especially chapters 4 and 5, and 6 for that matter. They're like, this is the equation for that. Like, there you go. If you want the proof, ask your professor, but I don't know those. So that general form of the equation is right there. It's 1 over 4 epsilon times the line integral of your charge, your line charge distribution over R prime. How far are you, right? But R prime is a variable. So we said that R prime is going to be, it's just hypotenuse of z squared and v squared. Just Pythagorean, right? It's just going to vary. So that's our general form, and to make it apply, we're going to put it in here. And in our case, our charge distribution isn't a variable of L, so we can pull it out. We can just pull it out front, doesn't matter. And then I just replaced R prime with this and put the length measurements in there. And if you do that integral, you'll get the expression for what it is. And then if I do in the midterm, if I give you some actual values for how long that line charge is and what the charge distribution looks like and how far away B is, you can actually give me a voltage. But as it's written in the textbook, the answer is just a expression. It's just solving that integral number-wise, which is kind of boring. I made some numbers on the midterm, or on the final. Can't keep things in my hands today. Questions on this? They get a little tougher after this.